jumping right back into it. Last time we did this handout, we talked about chapter 4. Chapter 4 was the x, p of x stuff, and then the binomial probability stuff. So we're going to have some practice over those kind of problems. My plan for today is to actually get through into chapter 6 a little bit. Chapter 5 has only got 2 sections. We're done with chapter 4, so we should be able to do that, and we're still on track. Let me make sure there's no questions from anything. Okay, all right. We covered the theory of like these x, p of x kind of stuff. So now there's a few homework problems that are related to what we're about to do, but it's just the actual immediate application. So let me ask you guys, is anybody out there over 25 besides just me? Okay, a couple of you guys. Do you guys remember what happened when you turned 25 related to your driver's insurance? Bless you, your car insurance. Yeah. It should have. I still remember getting my bill and going, oh, holy shit, it goes down like a decent amount. If you're not quite 25 yet and you're driving and you're paying insurance, there's a little something for you to look forward to. Does anyone have any idea why the hell that happens? Yeah.
Because I think you're more mature to handle the situation, so you're not reckless or irresponsible.
Yeah, sort of. It's not really. I like the way you put that. It's not really based on some people going, yeah, I think they're going to probably be. No, it's actually based on just hard numbers, right? If you're less than 25, you're more likely to get into an accident. If you're over 25, you're less likely to get into an accident. So somehow when you wake up on your 25th birthday, you suddenly know how to drive, right? So, well, no, obviously not. But it's just based on general situation, right? There's a ton of other shit, by the way, besides age. You can get a good student discount. Does anyone know about that? Most car insurances, if you turn in, I can't remember what kind of evidence you need to turn in, obviously some kind of transcript, something, they can give you a good student discount. And again, the reasoning is basically the same. The data bears out that the more you are, if you're in college and you're doing well, you're less likely to get in an accident than if you aren't. Does that mean that going to college and doing courses actually makes you a better driver? No. Not necessarily, right? And later this semester we're going to get into something called correlation. And I famously got this job here because partially I videotaped my lesson where I was talking about the number of beers you drank the night before and the grade you make on the next morning test, and to see if there's any correlation between the two. I made it really clear that it was not an experiment I was having my students conduct. So, but it's just an interesting thought process. Anyway, that's later. So let's focus on this. The way they calculate the amount of money that they're going to make you pay is based on things like people who are your age, people who drive as much as you do, people who blah, blah, blah. They look at the actual amounts that they had to pay out to cover whatever accidents they got into or were involved in or whatever, and saw the probabilities of those amounts. And then they actually made a table. They make a table. X's would be the amount of money they have to pay out for give it a certain person in a certain situation, and these would be the probabilities of those. So when you calculate, how do I calculate the average, the expected value in this case? What do I do to calculate the average if I have this situation? No, I think I heard what you said. You don't add them all up and divide by how many they are. Is that what you said? Yeah. No. Does anyone remember? I know it's been a couple days. Multiply across. And then you add them up. So the average. So the one reason we call this the expected value is because if I do something over and over, it's how much I expect to make or lose, if we're talking about money. Right? Very often this is talking about money. So let's do a concrete example of this. Okay, so insurance companies they'll put like $0. The probability they pay out $0. $100, they'll probably pay out that, right? You can probably tell it's a little more complicated, but it's basically built on this idea. Okay, I don't know if you guys are with me. And of course, if you're in a different situation, these probabilities change, which means these change, which means this changes. So if they calculate $400 for a certain kind of person in a certain situation, are they going to charge? So that means that's the average amount of money in a year or whatever that they'll have to pay for a good student who is over 25, let's say. You with me? So how much do you think they're going to charge you in a year? Are they going to charge you $400? Shit, no, because if they charge you $400, that means they're going to break even on average. So the average amount of money they would pay out for a person who is over 25 and who's a good student, let's say it's $400 a year. Does that mean everybody in that situation, they're going to pay $400? No, right? Some people won't get in any accident at all. Those are zeros. Some people will get in a lot of accidents. Those are whatever the hell. But when they average it, it's $400. So they're going to charge $600. Some people they're going to lose money on. I really want you guys with me. If they charge $600, will some people have more money they have to pay out than that? Yes. Will a lot of people have less money they have to pay out? So on average, they're going to make money. So for example, you walk into a casino. Has anybody ever gone into a casino? Okay, very depressing. Sorry, I'll go there sometimes. Thankfully, I'm not a gambler. I don't have any of that in me. I can just walk away easy. Otherwise, I'd never go into one of those places. But I just see these people just sit there. You know, you don't even do this anymore. You push your button, but and they just pull, and then they win, and they don't give a shit because they already lost so much money. But sorry. A casino. Let's say that one guy over there in the corner plays that big game and they win $2 million. Why does the casino not bat an eye? Why do they don't give a shit that just they had to pay this guy $2 million? Why do they not care?
They probably triple that, probably.
Yeah, that one guy. Well, then there's thousands of other people losing money. So on average, they're like they love that shit. They love it. They put that big ass machine at the front. The one that pays $1 million, because if somebody wins, everybody sees that shit, and they all get excited, and they pay more money, and they get the free drinks, and they're like, oh my, I can't think anymore, let me just skip it. All right, sorry. I haven't been to a casino in a long time, I don't know, but obviously it was traumatizing. All right, so, hopefully all that makes sense. Let's get a smaller scale, concrete example of what's happening. So let's say we set up a game where we give somebody a die, and they roll it. And if they get a 2, if they roll a 2, they win $10. Anything else, they lose $3. So now I'm curious, a person who plays this game, how much can they expect to win on average? If they play one time, do we know how much money they're going to win or lose? If somebody came along and rolled a die, do we know how much they're going to win or lose? They could win 10, they could lose 3, we don't know. But if somebody played a lot, if somebody played the game a lot, we could figure out on average how much they should win or lose. Does that kind of make sense? So let me ask you guys. So under the X, I'm going to put the value. So I could put next to your win, lose, but I need these to be numbers. So if I win, I make $10. If I lose, I lose $3. So if I lose money, you got to make it negative. Negative showing the direction is away from you. I like it. What do I put here for probability? What is the probability that we win? Yeah, there's one side of the die has a 2 out of 6 sides, so of course what's probably I lose? 5 out of 6. By the way, real quick, would anybody play this game?
No.
Did it cost money to play this game?
I'm sure people would actually play this.
To play the game, it doesn't cost shit. You could lose some money, But would anybody in here gamble with this game? What do you think?
Maybe like once or twice.
Once or twice, okay, because then you're like limiting the, you lose twice, you're out $6, but you had a chance to win 20, right? So, okay, so that kind of averages out. So we all, humans, we instinctively do this. I'll do another example in a minute and show you how we instinctively do this calculation. Not perfectly, because we're just freaking humans, but we have this intuitive feel for this kind of thing, believe it or not. So if I multiply across, I get 10 over 6. My suggestion to you when you have fractions, keep them as fractions. Don't reduce, because then you have all the same denominators, right? Be nice to yourself. So this will be negative 15 over 6. So when I get the average, the expected value, what do I get? What do I get when I add these up? Negative 5 over $6. Now, in exactly the same way that if I said the average number of kids is 2.5 and nobody freaks the shit out like, oh my God, the half a kid. We all understand that averages can be, if I have 25 kids and 10 parents, there's 2.5 kids per parent, right? We don't freak out. There's no half a kid anywhere. I cannot play this game and lose exactly 83.333 cents. Yes? That's what 5, 6 is if I did that right in my head. You guys semi with me? I can't do that. What does this mean then? For example, on average, I'm going to lose 5/6 of a dollar. So if I play this game 6 times, I should expect to have lost. Every time I play, I lose on average negative 5/6 of a dollar. If I play 6 times, how much should I expect to lose? Let's do it this way.
Negative $1.
No. Let's do it this way. Somebody double check me here. I'm pretty sure I'm right, but isn't that 0.833 repeating? Yeah. Yep. Thank you. Okay. Every time I play this game, I will lose 83 cents on average. Do I ever lose exactly 83 cents? Is that possible? Hell no. I can only make 10 or lose 3. On average, I'll lose 83 cents. If I play this game 100 times, how much money can I expect to lose?
$8.30.
100 times.
Oh, $83.
83 bucks. You just multiply that by 100. If every time I lose on average 83 cents, if I play it 10 times, I'll expect to lose this times 10, $8.33. On average, right? I really want this to make sense. In fact, watch this. If we play this game 6 times, how many times would you expect to win? Once. Is everybody cool with that?
Yeah.
Is that guaranteed? Well, am I guaranteed to win if I play this game 6 times? No. If I roll a die 6 times, am I guaranteed that a 2 will show up?
No.
You with me? There's no guarantee. The dice doesn't know, I haven't rolled a 2 yet. You know? You guys kind of with me? So what does it mean then? It means I expect to get 1, 2 out of 6. That's what I would expect to get. So if I get like 5 2s, and when I roll it 6 times, I'm like, what the hell's up with this die? Yeah, it could be loaded. Where did I get this die from? All right. So if what we expect to happen happens, I will win once and I will lose 5 times. Yes? And what's 10 minus 15? Negative $5. So, and look here, if I play 6 times and I lose 5/6 of a dollar every time I play, this tells me I should lose about $5. Really want this to make sense. So again, when the insurance company calculates, they add up the XP of X's for somebody in some situation, and they get a number. That does not mean that anybody will actually have that much money that I have to pay out for them. On average, that's what I expect to pay out. Therefore, I'm going to charge more than that to guarantee I make a profit. And they have a bunch of people employed keeping track of the probabilities so that they don't start to lose profit, right? You guys semi with me? Okay, sort of. Let me stop for a minute. Yes.
So with number 36.
Yes.
4.2, I'm at least trying to see how that would apply to this.
Real quick. Let me do one more, and then we'll do that specific example. This one's going to be a little less specific. All right, everybody. If you had a chance to win $1 million, right? But you had to pay $1 to play, but you could win $1 million. Would you play?
Yeah.
Now, what's funny is I haven't even told you the probabilities yet. But as long as there's a possibility I'll win, I might play that. Why not? It's just $1, right? Now, of course, for some of us, for me, there's definitely a period of time where $1 was everything. If I found $1, I'm like, oh. Yeah. So for a little while, Jeff in grad school was having, living a very plastic life. But if it only costs $1 and I might win $1 million, sure, I'll throw $1 at that. You with me? Okay. Does everybody agree with that? Like right now, if you didn't have to, now if you go, well, I have to go to freaking 7-Eleven, I have to go in there, and I have to get a thing, and I have to choose a number, then you start to calculate, screw it, it's not worth it, right? But if I'm here and I'm like, give me $1 and I'll give you this, and you could win $1 million. It almost doesn't matter what the probabilities are. You're like, yeah, I'll throw $1 at that one, no, right? Is everybody with me? What if I said you can win $1 million, but you got to pay $1,000? If you pay me $1,000, you have a chance to win $1 million.
Depends a lot.
Now I was hoping somebody would say, what's the probability, Jeff? Let me ask you this. Is everybody with me? Before I said the probabilities, I think most of you guys are like, dude, I don't have $1,000. You priced me out of playing this damn game, Jeff. But if you did have $1,000, would you play that game? I understand most of you guys were immediately no. What if I said the probability you win is 90%?
Yeah.
And it costs $1,000 to play. All right, now, do you guys? Some of you guys still like? I don't know. I really want you with me on it. There's no wrong answer here, really. Does everybody understand what's happening? So you pay me $1,000, you could win $1 million, and now I'm telling you there's a 90% chance you'll win. Some of you guys are like, shit, yeah, and some of you guys are looking like, I don't know what's going on, man. You need $1,000? Should I report you to somebody? My teacher wants $1,000. All right. No, I don't need your money. Let's do this. So if you could win $1 million, but you have to pay $1, right? Let's say the probability you win is 1 out of 100. Say you have a 1% chance to win. Are you with me? So if we set that up, now let me ask you this real quick. If I lose, what should I put here?
$1?
-1. This is gonna suck for the math, but too bad. If I win, what should I put here? Nope. Yeah, 999,999. Does everybody understand that? I give you $1 million, but then you have to pay me $1. So aren't you actually making 999,999? Okay.
Technically, yes.
What's the probability I win? Or that you win?
90%.
No. That's the second thing. Right now it's at 1 out of 100, right? And the probability you lose? 99 out of 100. Now this is kind of silly. Let's see what the expected value is. If I multiply across, and multiply across, and I add, what do I get? 999, 900 over 100. Yes? This is why, for example, what's the odds that you'll win the lottery? Does anyone know roughly what that is?
1.12 million.
Yeah, it's like the big one is 1 in 7 million, right? So if there was only a 1 out of 100 chance, I want you to understand what this means. on average, I would expect to make $9,999 every time I play. So what's really happening is we're gonna lose, win. And then overall, we will have made that much money on average. You guys semi with me? So in this case, if this is positive, whenever you calculate expected value, if it's money, if it's positive, that means overall cash will be coming in your direction. If it's negative, it's going to flow away. The bigger positive, the more you should do it. The bigger negative, the more a gambler would have to come into play and do it, right? And we're like, I don't know. I really want you guys with me on this. Okay. So what if instead, instead it was you had to pay real quick. This last one. Oh shit, this will change. What if instead you had to pay let's see, $1,000, right? You have to pay $1,000 to get a ticket. So how much will you actually win then? Yeah, okay. And let's say the probabilities are still 1 out of 100 chance you'll win, 99 out of 100 chance you'll lose, right? Okay. Again, you don't have to, I don't know if you're trying to copy all this. This is all just ideas. You don't have to copy all this shit. If I multiply across, add down, what do I get? So I get 999, wait. Yeah. 999,000 over 100 minus 99000 over 100. Yeah. And then you add them up. So now it's less. It's still positive though, to be honest, right? But again, so I have a positive expected value. What would this be? This would be 9,000. If I did that right. Which is a big if. Yeah, okay. So it's still positive, but it's a lot smaller than it used to be. But now you have to have $1,000 in the first place, right? So there's other considerations. So the more I've got to pay in, the less I'm going to expect to make on average. We all kind of intuitively understand that to a certain degree. Calculating these tables helps if I'm an insurance company. Then I want to know the exact number for the expected amount of money so then I can set the premiums to make sure I make a profit overall. And I want to employ a few people that are keeping an eye on the freaking numbers and say, hey, you should really raise those premiums, oh shit, to make sure I continue making a profit, right? Silly insurance. Okay, I like it. So long story short, when you turn 25, it's going to be great. So there will be some, so ask me a question about that number 36. What was that one about? Was it about picking a card?
It says you're playing a game by drawing a card from the standard deck and replacing it. If the card is a face card, you win $30. If it is not a face card, you got to pay 2. There are 12 face cards in a deck of 52 cards. Should you play the game?
All right, hold on, let me catch up to you. If you get not a faces, lose 2?
Yep.
So just intuitively, what if I said, here's a deck of cards, if you pick a face card, I'll give you $30. If you don't get a face card, you have to pay me $2. Would you play that?
Yeah.
Intuitively? Yeah. Again, a couple times, right? Why not? Throw some money at it. If I play a couple times, I'm out at most 4, and I have a chance to win $60. I mean, holy shit. So we kind of intuitively understand what's happening. Now, what if I would have said, instead, I say, if you pick the 7 of hearts, you win $30. If you don't pick the 7 of hearts, you lose $2. Now, we kind of have an intuitive sense, it's less likely that I'm going to win. I'm more likely to lose money. Maybe I'll throw still a couple if I'm okay losing $4, so maybe I'll play it a couple times, but I'm like, I don't know. Okay, maybe. So intuitively, we are able to sort of put things together. How much could I lose or win? What are the probabilities? But we definitely don't do it exactly, right? So how would I do this exactly? And this one, I didn't have to pay to play, right? It didn't say you had to play to play? Okay. So win, lose. So if I win, positive $30. If I lose, I'm out $2. The probabilities are based on the situations that leads you to win or lose. Now they tell you in the problem, but you guys know how many cards have a face on them?
12.
Yeah, there's 12, there's the king, jack, and queen, just to put them in a weird order. So there's 12 out of 52 that will have you win. So how many will have you lose? 40. And now if you calculate x times p of x, you can actually see, is the expected value negative? Is it positive? If it's negative, is it really big negative? If it's positive, is it really big positive? So I think there's two problems that are kind of like that. And I think one of them you have to pay. If I had to pay $3 to play this game, then I would just take 3 away from each of these, right? And that would really suck. You got to pay to play, and then there's a chance you lose more money, right? Okay, maybe. Is that better? So there are two problems in there that sound sort of like that. If you set up the x, p of x tables, you just calculate the expected value. That's going to be what tells you the answer. So you just multiply across, add down. So whoever set up this game, did they do a good job? Well, let's see. What do you get when you multiply across here? You get 30 times 12 is?
30 times 12 comes out to 6.92307 altogether.
Well, if you divide by 52, but that's just 360. And then negative 2 times 40 is negative 80. So if I keep them in fraction form, I could just add them together. I get 280 out of 52. Is that positive?
Yes.
Is it relatively big positive?
Yeah.
Yeah. Whoever set this game up is not smart. They did not take this class. What would make this a fair game? What should I get here if this was going to be a fair game?
50-50?
No. Probabilities don't have to be 50%. What should I get for the expected value if it's fair?
0.
0. Fair would mean you don't make money, I don't lose money. You're playing my game. Fair would mean nothing, which is not interesting at all, right? This is so not fair, but it's not fair for the house, which is really bad. Are you kind of with me? Whoever set this game up does not understand probabilities or anything. Okay, maybe. What if I adjusted this to be, you have to get a 7 of hearts, right? That's a heart, believe it or not. Bless you. And if I don't get a 7 of hearts, then I lose $2. What would happen to the probabilities?
Negative 50 out of 52.
What? 7 of hearts. How many 7 of hearts are there? 1 out of 52. How many are not 7 of hearts? 51 out of 52. Now it's going to be 30 over 52 minus 102 out of 52. Now, if I'm setting this game up and I have many people play, I'm going to expect to make money over time. Even if a few people win, a lot more people are going to lose. Just like the casino, right? Okay, maybe. There was a movie, it's called A Year of Living Dangerously, where the beginning of it is basically this guy who's in a casino, and he says people mail money to them so that they can save money on the airplane ticket, right? Because they're like, I'm going to lose money. Sorry, this is a bad joke. Too bad. Yeah.
I was going to say, because I added up what I got from the x times p of x. I added both of those numbers up and I got 5.38462.
For this?
Yeah.
Oh, or for the problem you're doing. For this?
Yeah.
So you got negative 5 point, right?
I got negative, so I got for 30 times 12 over 52, I got.
Oh, the one before. I see, okay. Yeah.
Yeah.
The one before, when I had it for face cards, that would be, you would expect to win $5 and whatever.
Yeah.
So holy shit, you would play that game a lot. Holy shit, right? I'm going to play the game a lot. This game, again, I might play a couple of times, but the payout's not really, make the payout $100. Now we're starting to get there. But all right, I'll stop. That's enough. There's enough. So there's a lot of factors. How big is the payout? How much money does it cost to play? What are the probabilities? And we have this intuitive sense of when it reaches a level where we're like, okay, I'll play, or when it's like, no, I don't think I'm going to do that shit. But this is what makes it more concrete. Okay, I'll stop. Now, So again, it's number 36, and I think it's number 72?
70, it says, if Theater Group
70?
holds a fundraiser.
Yes.
It sells 100 raffle tickets for $5 a piece. Suppose you purchase 4 tickets.
Yes.
The prize is 2 passes to a Broadway show worth a total of $150.
Okay. So again, when you set it up, the X column should be the amount of money. In this case, it's like a value that you're gonna make. If you had to pay money, it should go down. So I would expect, if I win, I get $150 tickets, but I had to pay $20 to get them. So I would put 130 under X. Does that make sense? If the prize I'm gonna win is $150, but I had to pay $20 to play, then I'm gonna put 130 under the X column. And the probabilities are based on how many tickets win. In this case, what was it? 2 out of...
Two passes to a Broadway show. It says 100 raffle tickets.
So 2 out of 100 chance. 2 tickets win?
Yeah, you said 130?
Yeah, because the value of the tickets is $150, but you had to pay $20, didn't you?
No,
Yeah.
100 tickets for $5 a piece.
By how many tickets did you buy?
Oh, 4.
Okay, cool. All right, maybe. All right, enough of that. You guys, when you get to that problem, we'll see how it goes. Okay. So, moving on. So we pretty much, we finished chapter 4 last time, but just to remind you guys, it should be insanely obvious when you're supposed to use this formula and this formula. These are our 2 new formulas from 4142. Should be really obvious when you use them because I'm going to give you x's and p of x's, right? Okay. The other thing we did, bless you, this is 4142. The other thing we did from 43 was the binomial distribution. I also call this an NPQ problem. They should be, and again, I keep saying like, it should be obvious when you're gonna do this. Here's what to look for so you know when to do this. Because one of the hardest things in all of mathematics is, when do I do which thing? Yes? I know how to do that, but when the hell do I do that? Okay, yes?
Is the standard deviation formula
Bless you.
the same for the population and the sample?
You'll notice in this situation, we're assuming it's a population.
Okay.
And the reason we have to do that is, what's on the bottom of the probabilities? Remember that? What's on the bottom of any probability? N, right? The total number of things. What would it have to be if I wanted to be a sample standard deviation? N minus 1. And see, and so these will always be population stuff. Okay, I like it. Binomial, I call them NPQ problems. So it would be any situation where I say 87% of people do this. Well, automatically 13% don't. There's P and Q. If I take 82 people, okay, there's N. So if you can identify N, a probability of success, and the opposite of that, the probability of failure, that's an NPQ problem. I'm going to use these formulas here to calculate the mean and the standard deviation. And then of course we got this. Okay, I was about to say mamma jamma. Why not mamma jamma? This thing right here, which is the probability of something, right? So, and again, this, I can read this. This many people choose this many to succeed, so I got this many successes and the rest are failures. I mean, it just reads as a sentence. Okay, I like it. Okay. I always feel like you feel like I did in my French class when my French teacher was French too, and she just spoke French.
Oh,
And I'm like, holy shit.
was that just like a high level French class?
No.
Oh, damn.
She just was, just the way she was. The phrase I know a lot in French is fermer la bouche. Anybody know what fermer la bouche means? Close your mouth. So we were a very talkative class. Anyway, so these are the brand new formulas we got from chapter 4. And I really try to show you, what do you look for so you know when to do what? Okay. What does this formula calculate here? What does that formula calculate? What does this mean?
Probability of X.
Probability. The probability of getting so many successes. Okay, maybe. So we're gonna do, in fact, let me do this. Let's do this immediately. Yeah, beautiful. So one side's got a lot of funky stuff happening. It's got a little pyramid going on. Don't worry about that side yet. All right, let's see. All right. Okay. So if you look this over real quick, and again, we'll talk about this side in a minute. Don't worry about this side. We'll look at this side here for now. And most of my handouts were last updated within the last decade or so. So I don't know if this is still roughly true, but let's go off of this. So a while back, I saw there was an article, there was a report done about the percentage of U.S. college students, how well they feel about speaking freely on campus. So a while back, it was 68% felt that the campus climate prevented people from speaking freely. We randomly choose 22. So already, I get the sense that this is an NPQ problem. A certain percentage feel a certain way, so a certain percentage don't. They give me a total, okay, that's N. I already see N and I see P, and I can figure out Q. So it's an NPQ problem. So I wanted probably exactly 13. So somebody help me out. What's N? 26. Yeah, 26. No, not 26, 22. So we choose 22 students. What's P? 0.68. And what's Q? 0.32. Kick ass. Say again? Yes, beautiful. X 13. So now I want the probability that I get 13 successes. So take a minute and try to set the formula up, and then I'll catch up to you. Oh yeah, anybody needs a calculator? Oh, well I think that should get you through. Gotta start recharging those things, all right. All right, let me catch up to you guys. What'd you put here? 22. I got 22 people. I want to choose 13 of them to do something. So I want 13 of them to do this, and how many to do the other thing? 9 of them. I love it. So what's got to be true about the two exponents in that equation? They always have to add up to be n, the total. Kick ass. So let's see if we remember how to put all this stuff in the calculator.
0.11.
I like it. So if you forgot 22, math, probability, choose 13, hit the over arrow to come back up, times 0.68 to the 13, hit the over arrow to come back down, times 0.32 to the 9. Beautiful. Or you could put 11.63%, either way. Wee-haw. Essentially, anytime I ask you a probability question, you need to show work, and then you have to show me the answer 4 decimal place thing. You know, if the answer is 10%, you don't have to put 0.1000 there. You happy, Jeff? No, just put 0.1. That's fine. Okay. Why, if I do part B, why is it wrong if I just put a 21 here and then stop? It says less than 21. Shit. So what is less than 21? Less than 21 thinks so. So what could that mean? It could be 20. I'd have to do the formula for 20. I'd have to do the formula for 19. I'd have to do the formula for 18. It's a 0. Do you all understand? To get the probability of a situation, I have to add up all the probabilities that situation references. So I'd have to do the probability of each of those and add them up. That would so suck. There's a shortcut.
We could just do the probability of, so that it's saying less than 21. So we could just do 21 or 22.
Beautiful.
And then
What is the opposite of less than 21? In this situation, what's the opposite of less than 21? 21 or 22? So this is a general idea. This isn't just about at least one, but that is the most common thing to see that leads me to do what we're about to do. Any damn time, the question involves a lot more work than the opposite question would involve, I'm gonna do the freaking opposite. Right? And I like to joke around that the question's angry and then I do 1 minus them, like, there you go, question. Shit, there's your answer. So we calculate the opposite of what the hell this thing's asking me. Why do we do that? A lot less freaking work, because then I could just do 1 minus. Right? It's exactly the same as probably it's gonna rain today is 10%, so probably it's not gonna rain is 90%. So if I calculate the opposite of what this guy wants me to do, and then I do 1 minus what I get, it will answer the question. So instead of doing probably 0 plus probably 1 plus up to 21, 22, well, I would do up to 20, right? But if I add up all the probabilities, I get 1. So if the sum of everything up to 20 is 1 minus these two things. So what's the probability of 21? What would that formula look like? "22 people, choose 21 of them. So I want 21 successes, and I want how many failures? If 21 of them succeed, how many fail? 1. Okay, maybe. So can you guys, don't say anything, just real quick put that in your calculator. Yeah, so I get 0.0021. I so desperately want you guys to understand that. It kind of feels nice. In mathematics, the question says, figure this out. And you're like, no question. I'm going to figure out the opposite of what you want. Nah. So then I still have to calculate the probability of what? 22. So that'd be 22, 0.32 to the 0. So the shortcut is just to do 0.68 to the 22. We talked about this before because there's only one way to choose 22 from 22, and anything to the 0 power is 1. Or you can throw the whole formula in there, doesn't matter, the calculator will still come out with that answer. What does that answer mean? Is that answer 2.066? If you put 2.066 down as an answer to this, why should that immediately be a red flag? What are we calculating right now? The probability. And what's the biggest the probability can be? 1. So that would be an immediate red flag. You don't write that stuff down. It's E negative 4, so that's going to be 0.0002. So if I add those together, what do I get?
0.0023.
That is the answer to the opposite question. So now if I do 1 minus that, I'll answer the actual question. So very often, if you see me say at least or at most something, you got to stop and think, would the opposite have less work to do? I'm going to do that. Okay. So what is 1 minus 0.00? It'll be 0.9977, yeah. So almost 100% chance that less than 21 of them. Which makes sense, because in any group, what percentage would think that way? In any group, what percentage would think that they're prevented from speaking freely? 68%, yes? And 21 out of 22, I mean, so yeah, it should be. I would expect less than 21 of them to think that way. It should be really unlikely that 21 out of 22 think that way, because there's only 68% chance they think that way. Okay, so that's why this makes sense. At almost 100% chance that we'll have less than 21 people feel that way. Okay, maybe. Okay. Yes, I did. Cool. So here, you guys try to do part A on this number 2. All right. So let's see. So I have 211 So what's going to be the power on the 88%?
92.
Okay, I'm going to trust past Jeff. There's a certain point where the numbers make the calculator freak out. Pretty sure I didn't make this go there. Yeah. Anybody get that number yet? Yeah.
0 through 16.
So not quite a 4% chance that exactly 19 out of 211 U.S. workers will feel that way. Okay. I'll lock it. So it's fine if you want to make this 3.62%. What was the formula for the mean in this situation again?
NP.
Yeah, it's the best formula ever. And then square root of NPQ for the standard deviation. So figure those out. Let's see. No, Jeff. There you go, buddy. So I get 25.32. So let me ask you this question right now while I got this up here. The probability of 19 successes was relatively small, right? What do you think would make the probability the highest? How many successes would make the probability the highest?
0?
No.
12%.
No. If I made this x equal 18, would the probability go higher? If I made this x equals 107, would the probability go higher? Let me see what you guys think. What was the average we just calculated? What was another name for the average? Starts with an E. Expected value. Okay, so let me ask this again. What value could I put here that would make the probability the highest?
26? Or,
I see what you're saying. Yeah, somewhere around 25. Because what do we expect? If I, out of any group of 211, on average, how many people out of that should I see? About 25.32. So that should have the highest probability of happening. To be honest, the actual maximum is close to this. It isn't necessarily exactly equal to this, and obviously it's because it's got a little bit of a decimal going on. I don't know if you guys are with me or not. So I would expect that much. Again, if I make half of my free throws and I take 20 free throws, how many do you expect to have happen? How many should I make? If I make half my free throws and I take 20, you expect 10, right? So on average, I should make 10. So on average, I should expect 25 to show up, around 25. So if we did this formula for 25, it's going to be quite a bit higher than that. It should be around the highest it could be. Maybe. So that peak, the tallest bar, should occur right around the mean. Okay. So now if I do this, it should be 211 times 0.12 times 0.88.
4.720.
4 point?
Yep, 4.720.
720? Neato. Everybody else got that? Yeah? Okay. Now who remembers, so again, right now, this means that this is what I would expect on average, but of course, if I just pick a random group of 211 people, it's not going to be exactly 25. If I flip a coin 100 times, will I get exactly 50 heads? Hell no, right? In fact, real quick, while I'm on that, if I flip a coin once, what sense does the probability of getting ahead 50%, what sense does that make? Am I getting half ahead? So any probability really only makes sense in the long run. If I flip a coin 1,000 times, the first thing is, what the hell am I doing with my life? But the second thing is, how many heads would I expect to get if I flip a coin 1,000 times?
500.
Now, if you got exactly 500, wouldn't that be a little bit freaky? But you expect somewhere around 500, correct? You guys with me? So if you flip a coin 1,000 times, and you're okay with the fact that you're doing that in your life, and you get 490 heads, will you freak out?
No.
What if you get 400 heads out of 1,000? Will you freak out? What if you get 100 heads out of 1,000? Is that evidence of something? What do you guys say? I really want you, right? If I flip a coin 1,000 times and I only get 100 heads,
So weird.
that's weird, yes? You guys agree that that would be unusual? Oh, shit, yeah, I see what you're doing. Bring the definitions in. All right, sorry. So we have an intuitive sense, again, the further we get away from what we expect to happen, the more unusual it is. So in a court case, when they say within a reasonable doubt, that's what they're talking about, right? So 490 out of 1,000 heads, that's within a reasonable doubt. That's near what we expect. 100 out of 1,000, no. DNA match of blood found at the scene. Is that 100% that was you? Do you guys understand? That's not 100% but that was you, but it's within a reasonable doubt, right? Okay, maybe. Okay, I love you guys. Okay. So, how do I get those min and max usual values? Where does unusual start? How far away do I go? 2 standard deviations. I love it. So if I start at the mean and I go down 2 steps, this will be the min. Where do I end up? What is that? 15.9 something. 15 point something. 15.8. Somebody save me from myself, please. 15.78 roughly. Okay, thank you. That is the minimum, and then the max is just adding 2 steps. Oops. Uh-huh. 54. So 34.86. Darn it. Okay, so close. So would it be unusual if we did pick 211 U.S. workers and we found 14 that worried? Only 14. Would that be unusual? And this is not a subjective question. This is objective, now that we've defined what unusual is. So in our everyday life, we don't have a hard set definition. Just like we saw a second ago, was 490 unusual out of 1,000 if I get 490 heads? No. Was 400 unusual? Is 100? Yeah. So somewhere, there's not a clear line of where it's okay and then where it starts to get weird. There's not, but mathematically, we can kind of like set some things. So now, is 14 unusual? Yeah, it's unusually low, correct? I expect somewhere between this and this. So if we get 14, that's unusual. To be specific, unusually low. So real quick, do you guys know the name Aaron Brockovich?
Yep.
I know the last name.
Okay. So a while back, there was things about PG&E that had contaminated water. It was causing people to get cancer, but they had to kind of prove it. So in any group of people, I expect the rate of cancer occurrence to be between this and this, and I can calculate it using this mathematics. So if I go to an area and I see an unusually high occurrence of cancer, number one, does that automatically mean something weird's happening there? No, it isn't. But if I couple that with water that I've analyzed that does have higher than normal amounts of whatever, now we're starting to develop a case. Yes? I really want this to make sense. So calculating what is usual and then going to see where is it unusual is sort of like a first step. Your first step in an investigation is it out of the ordinary? And then you start to look at the specifics. Is it the food? Is it the water? Is it the air? Is there a factory nearby? Is somebody dumping stuff here? Right? You guys kind of with me? It is possible. In fact, statistics says it must happen that there will be groups that just kind of randomly have a higher occurrence of cancer. It just will happen. But if it's also in conjunction with water that's got weird shit in it and the air is bad or whatever, then you start to go, okay, now we got to tell this factory to kind of like shut that shit down, right? Okay. You get those three-eyed fish, and you're like, okay, wait a minute. Okay, maybe. I love you guys. So, because one of the first things we think of when we really think about statistics is it's been clinically proven that this will, and this is kind of like the first steps of trying to trying to find evidence for something. Okay, this next thing we can't do yet. Don't worry about Jeff finding keys. That's a little early. You guys want a break right now, or you want to? All right. I think I see a few more people shaking their head yes than no. So let's take a break. Come back at 10:20, and then we'll get back into it. I'm trying to let us out a little bit early. We'll see what happens. So come back at 10:20. If you need to see me for any reason, come on up.